Hi, everyone. Thank you for joining. We'll get started in just a few moments, so hang tight. For those of you just joining, hang tight. We'll get started in just a few moments. Thank you. All right, we are going to go ahead and get started. Thank you all for coming today. I hope you had a nice holiday break and New Year. And welcome to the January 2024 edition of Green Infrastructure, Climate, and Cities, a monthly seminar series focusing on the unique challenges that climate change poses for cities and what we can do about it. My name is Nikki Pearl, and I'm the manager of the Sustainable Water Resource Engineering Lab at Drexel University and the seminar series coordinator for the Consortium for Climate Risks in the Urban Northeast, a NOAA-funded team of researchers and universities investigating climate change's impact in the Northeastern United States. If you're joining for the first time today, CC Run began hosting this series back in 2014. All of our seminars are live cast, recorded, and archived on the CC Run website, which is currently being updated and is set to relaunch later this month. So please feel free to go back and watch any of our previous seminars there. Continuing education credits for professional engineers are available to for all of our seminars, and members of the American Institute of Architects are eligible for continuing education credits for this three-part series as well. Finally, as a reminder, please use the Q&A box to submit questions, as we will have a moderated Q&A session following the presentations. Next slide, please. So I'm excited to introduce to you all this three-part series in collaboration with the New York City Panel on Climate Change. Ahead of the release of the NPCC's fourth assessment, we will use the January, February, and March seminars to introduce each major chapter of the forthcoming assessment, its key messages, and implications for New York City. Today, we have Drs. Radley, Horton, Luis Ortiz, and Franco Montalto, who will be presenting on climate projections and flood risk in New York City. In February, we will cover climate equity and New York City futures, and in March, we will discuss health and energy implications of climate change in New York City. The registration links for February and March will be sent out through all of our communication channels in the coming weeks, but for now, I will also put the links to those in the chat. Okay, next slide, please. Thank you. Like I said, today we welcome Drs. Radley, Horton, Luis Ortiz, and Franco Montalto, who will be presenting on climate projections and flood risk in New York City. Next slide. So first, I'd like to introduce Luis Ortiz, who is an assistant professor with the Atmospheric, Oceanic, and Earth Sciences Department at George Mason University. He is also co-chair of the Climate Science Working Group of the 4th MPCC. His research centers on advancing our understanding of how cities interact with the atmosphere in the context of a changing climate and the impacts these interactions have on people and infrastructure. His work considers cities as complex systems of environmental, human, and engineered domains, and aims to consider all three as critical to understanding the impacts of climate change, as well as adaptation and mitigation strategies. He earned his PhD in 2018 from the City College of New York, studying building atmosphere interactions under extreme heat. He then joined the Urban Systems Lab at the New School from 2018 to 2021, where he worked on socioeconomic impacts of climate change in cities across the Americas. Before joining George Mason University in 2022, he completed an appointment with the Office of the U.S. Secretary of Transportation, where he worked on climate policy, environmental justice, and environmental permitting transparency. Next, I'd like to introduce Dr. Radley Horton, who is a professor at Columbia University's Climate School and is the principal investigator for CC Run. His research focuses on climate extremes, tail risks, climate impacts, and adaptation. Radley served on numerous national and international task forces and committees, including the Climate Scenarios Task Force in support of the 2018 National Climate Assessment, and he often appears on national and international television, radio, and in print. Radley also teaches in Columbia University's Sustainable Development Department. And last but not least, I'd like to introduce Dr. Franco Montalto, who's a civil engineer interested in the development of ecologically, economically, and socially sensible solutions to environmental problems with a focus on sustainable water resources engineering and climate change. He's currently a co-PI for CC Run and is a professor at Drexel University, where he directs the Sustainable Water Resource Engineering Lab. He's also co-chair of the Flooding Working Group of the 4th NPCC. Previously, Franco served as a research fellow at the Earth Institute at Columbia University and a Fulbright scholar in Venice, Italy. His degrees are from the Cooper Union for the Advancement of Science and Art and Cornell University. So thank you to our speakers for joining us today. Next slide, please. So here is a quick look at today's agenda. We will start by giving a brief overview of the NPCC. We will then cover updated climate projections for New York City, followed by flood risk. And then we'll briefly share links to other city efforts before closing with a general discussion and Q&A session. So with that, I will hand things off to our speakers.
Thanks so much, Nikki. I just want to, before we jump into the presentation, just talk about how exciting I am to, through CC Run, host an NPCC event like this one. There's a long history of collaboration between CC Run researchers and NPCC, previous panels of NPC, as well as the current panels of NPCC, especially going back to, and probably predating Hurricane Sandy, but I know there was a lot of Sandy research that happened through CC Run that fed into previous, into New York City policy associated with that particular event. Radley, I don't know if you want to say anything else before we kick it off about this sort of relationship between CC Run and NPCC.
Thanks, Franco, and all for the chance to speak here today. No, I think that's great. That really covered it all. I mean, the only thing I guess I would say in addition is that the diversity of CC Run perspectives and the funding provided by NOAA through CC Run, I think, has given us within CC Run, the researchers, some flexibility to try to sort of keep up, frankly, with New York City's journey, as it experiences everything from additional climate hazards, think of the focus today on compound extremes, for example, to really getting beyond the initially maybe sort of somewhat technocratic infrastructure focused takes on climate impacts and resilience of, say, 10, 15 years ago, which of course were an excellent start. But one thing to really commend is how the focus has expanded to include communities, environmental dimensions, more nuanced takes on health. So as the city has been on that journey, I'm very proud of how CC Run, I think, with support from NOAA, has been able to, in some small ways, sort of contribute to those perspectives. So with that, I think I'll turn it over to Luis, who's really, along with Christian, led so many of these efforts this time around with NPCC, perhaps most centrally around the climate science, which he'll start walking us through, and then I'll come in for a little bit, and he'll sort of bookmark the climate science component. So with that, Luis, over to you.
Thank you, Radley. And thank you for that great sort of overview to you and Franco of the sort of connections between CC-RUN and MPCC. So the New York City Panel on Climate Change has been around for over 10 years now. It was institutionalized in New York City through Local Law 42 of the year 2012, with a set of mandates that are encoded in this law. Essentially, having convening the panel every certain number of years in order to, one, prepare and help mitigate to the impacts of climate change and extreme events and how they're affected by climate change, help inform planning activities and investments in New York City, as well as amplify other efforts around climate mitigation and climate adaptation. And finally, and maybe most critically for some of the work that we're talking about today, to sort of provide a sense of the state of the art of the climate science and actionable climate risk information for New York City. And part of this is essentially doing an exercise very similar to what the IPCC with the National Climate Assessment does, in doing an overview of the state of the art of the literature and the existing science out there. But the MPCC also has a sort of a special mandate, and in particular, the Climate Science Working Group has a special mandate in developing what we call the projections of record for the city of New York to help inform a lot of these planning activities. Every 3 years, I believe, or every certain number of years, the city selects a panel, and each member of the panel and together sort of convenes various working groups covering topics ranging from climate science to flooding to equity. Next slide, please. So what is sort of the relationship between this assessment that we do here in New York City versus some of the other sort of different regional and even state and national scale assessments happening sort of at similar timeframes right now? Well, one of them is the coverage in spatial extent. The New York City panel focuses specifically on the 5 boroughs of New York City, while the New York State Climate Impact Assessment, which is carried out by New York State and covers New York State. Meanwhile, the National Climate Assessment covers the entire country and segments them by region, with New York State, the city of New York State being within the Northeast chapter. And the idea is, even though all these efforts perform sustained assessment and doing this sort of ongoing monitoring of the state of the science and evaluating climate impacts, they each sort of have different coverage areas and are able to provide different levels of detail regarding all these different areas. Next slide, please. So we have sort of this history of sustained assessment, and we're currently in the process of finalizing and rolling out the 4th New York City Panel on Climate Change in 2024, which sort of continues the sustained assessment of the state of the art of the climate science, using that state of the art of the climate science to update or confirm previous projections of record, and using that information to keep informing adaptation and mitigation policy planning and action in New York City. We do this by continuing this sort of level of sustained assessment of the literature, essentially updating some of the new science that has been released or published since the previous assessment in 2019, and essentially bringing in new data sources and new methods to update those projections of record. The way we go about this is as I mentioned before, we break up our analysis, our assessment into various working groups, which each develop a chapter or a report, which has historically been published in the New York Academy of Sciences. Each of these covering a topic that is decided between the panel members and through interactions with the city and other stakeholders. Next slide, please. And given that, we're going to sort of move on, and I'm going to pass the baton to Radley to sort of go over some of these updates to the state of the climate science, the new predictions of record that we have for New York City, and then moving a little bit into some of our key messages and some of the existing gaps that we still have. Radley, over to you.
Great. Thank you, Luis. Yeah, so what I'll do is just talk a little bit about some of the methods that were used for the projections, and then go through especially the sea level rise projections and some of the qualitative takeaways, followed by the temperature projections and some of the qualitative takeaways, and then finally doing the same thing for precipitation. Now, who would advance the slides? Because that's not something I do, right? Great. Okay.
I'm doing that, Radley.
Oh, okay, great. Thank you, Franco. If we could go forward one more. Great, fantastic. Okay, so as we jump into talking about these projections, which, as Luis said, really are an iteration sort of based on the latest climate models, which of course improve as computing power improves, and as we observe more about the climate system, right, our physical understanding kind of grows. But one thing I always nevertheless say when talking about climate projections is that we should understand that these are really just incremental improvements each time there's a new iteration of the NPCC. And to be totally honest, we can't even say this round of projections are quote unquote, better than the last round. They do represent innovations. And with the update, it's our updated sense of sort of the most likely range of probable outcomes for sea level rise, temperature, precipitation, other variables. But the bottom line, as anybody who's kind of been watching the exceptional weather we've been experiencing in 2023, for example, knows, there is deep uncertainty about just how much the climate is changing. And we need to acknowledge that while these climate models are our best tools, we're starting to see some outcomes, as I'm sure you all are aware of, that look a little different than what any climate models sort of tell us are possible. So it's uncomfortable to live with that kind of uncertainty. And it doesn't, of course, reside only in the climate projections. It resides across all the aspects of all that the NPCC aims to do, and indeed for sort of all planning that a city like New York needs to do. So think of these climate projections as our best estimates given the science available, but really the large uncertainty bounds are as much the story as the specific quantitative projections are. And it's a one-sided uncertainty, right? We know the climate is changing. We know the statistics of heat waves, coastal flooding, heavy rain events are changing dramatically. They're increasing, right? The uncertainty is about just how much are they going to change in the future. And that, unfortunately, is an inescapable uncertainty right now. So we need to plan in a robust way for the possibility and indeed the likelihood of a rapidly evolving climate that most of our systems simply aren't adapted to. Okay, so with that caveat out of the way, here is our sort of best sense. And we could, again, we could just go, yeah, perfect. Stay on this slide. So what we did is we used these latest climate models, 35 different ones, from the latest, what's called the CMIP, the sort of global models that are available. And we use two different, what are called SSPs. These are basically inputs to the models that make certain assumptions about how much greenhouse gas and other aerosols and things that force the climate, that change the climate, are going to be present. And we really focused on two of those. One, which is this SSP 4.2/4.5. That's arguably a path that we're sort of roughly on. One could debate, what path we're likely to be on. What are the future of emissions going to be? But it could be something close to that 4.5. But we also used a scenario called SSP 8.5, which most people who study greenhouse gas emissions would tell you is exceptionally high, and that it's unlikely we're actually going to live in a world that sees emissions increasing at the rate that they do in SSP 5 8.5. That said, these are scenarios. Our goal is to capture the range of what we think is the most likely set of future sea level rise, temperature increases, and precipitation. And frankly, as I alluded to earlier, there's so much evidence emerging that our climate models aren't sensitive enough to a given increase in greenhouse gases. So essentially what we're doing here is looking at a scenario, this SSP 5 8.5, of very high, probably unrealistically high emissions of greenhouse gases. But the reason we're doing it is A, because it can't be completely ruled out from a risk management perspective, but more importantly, because there's so much emerging evidence that you need to turn the dial up high in order to sort of make up for the fact that climate models, if we use a lower assumption about greenhouse gas emissions, aren't going to be sufficiently sensitive. They're not going to increase heat waves enough. They're not going to increase heavy rain events enough. They're not, frankly, going to give you enough sea level rise. So basically, it's an inexact science here. We're turning up the dial and considering one scenario, which I think quite plausibly is unrealistically high on the greenhouse gas emissions, but we're doing it because we're almost as confident that climate models underestimate just how much the climate might change with a given increase in greenhouse gases. So that's the rationale there. Again, it's a risk management perspective. So we have these two different SSPs or scenarios for how much carbon dioxide and aerosols we might see in the future. And we use 35 different climate models, each of which physically evolves the climate system in different ways based on those emissions of greenhouse gases. So one climate model may move the storm tracks a little further north than others. As a result, that climate model might have a different change in precipitation in a given season than another climate model. Using a lot of climate models and two different scenarios for future greenhouse gas emissions, we get this range of possible outcomes for planning. And then we have this historical baseline period that we use, the relatively recent 30 years from 81 to 2010. We use a slightly different baseline for sea level rise. And then the projections are relative to that historical period based on feedback we received from NPCC and New York State stakeholders. Very important to emphasize that this work was really made possible by funding from NYSERDA through the statewide assessment. And through a lot of feedback that we got through a needs assessment that we did, it was clear that projections centered around each 10-year period, so each decade, 2030s through the end of the century, were needed, whereas in the past, the NPCC, of course, just did 2020s, 2050s, 2080s as these sort of 30-year periods. So it's still centered around 30 years, but now you can kind of pick your decade and take a 30-year period centered around that decade. Okay, so with that sort of quick background on the methodology, and we can talk more about this if there's interest in the Q&A, let's jump into looking now at some of these projections. Okay, great. So starting out with the key messages around sea level rise and storm surge, after which we'll show some of the quantitative sea level rise projections. The overall takeaways, no real surprises here. We are committed to long-term sea level rise. There is a long delay between when you emit greenhouse gases and how long sea levels will keep rising. As a result, even if we could somehow miraculously turn back greenhouse gas emissions, we're going to continue to see sea level rise for a long time, in large part because some of the land-based ice sheets have begun to be destabilized to some extent, undermined in ways that it takes decades to centuries to fully manifest. And so a lot of those lags are in the glaciers and ice sheets, and those also are the dominant contributors, those glaciers and ice sheets, as some of that ice currently sitting on land increasingly makes its way to the ocean, where it displaces kind of existing water. Important to keep in mind that coastal New York City is experiencing a slightly higher rate of sea level rise than the global average. So that's something to keep in mind too. And then really arguably, I'd say sort of the most important takeaway is this fourth bullet here. Sea level rise, even if it doesn't sound like much, right? The sort of foot or so that we've experienced in the last century might be smaller than the sort of tidal cycle between your typical high and low tide in New York City. So you might be tempted to say, how could that foot over the last century really matter? But it matters an enormous amount. And the reason is because if you raise that baseline by a foot, you profoundly shift the statistics so that the high water levels that happen during the occasional storm or the astronomical high tide every month or every year, if we basically add a foot of water to that, we suddenly have the events that used to be very rare happening many times more often than they used to. And additionally, you start to experience unprecedented high water levels due to that extra foot, leading to extra damages, in some cases, loss of life. So that point is independent of the question of whether storms themselves and storm surge being the amount of water piled on due to a storm will change with climate change. There's a lot of evidence suggesting that we might see more powerful hurricanes, if you average across 10, 20, 30 years in the future. That would mean more storm surge in addition to the effect of sea level rise. But here, the point we're making is just that we're locked into additional sea level rise, and that in itself is going to mean that your high water levels associated with even the storms that we got in the past, if those continued, the high water levels would occur much more often and be much more damaging with deeper water than you'd otherwise get. And then, this last point may sound sort of like too much of an opinion, but the idea here really being an effort to get to the point that from a risk management perspective, you don't just consider the most likely outcome, right? If we're thinking about our power plants, if we're thinking about our vulnerable communities, if we're thinking about certain assets that we just sort of can't afford in a variety of senses to see damaged, we really have an obligation to consider low probability outcomes as long as they would be high consequence should they happen, which of course sea level rise and storm surge actually are. So that's the rationale for this statement about stakeholders needing to consider plausible scenarios at the upper end, whether for sea level rise or temperature or precipitation or any other variable. Okay, great. Go to the next slide. Okay, so now here are sort of the latest updated projections for sea level rise. Again, foundationally from this work that NYSERDA graciously made possible. So as in the past, you see these percentiles. That's trying to capture this range of outcomes. You could think of the 10th through the 90th percentile as not the full range of possible outcomes, but a pretty broad set of what we think is possible. And this, we should say, borrows very heavily from the approaches that are being used by the IPCC, but it's not identical. There are some adjustments, including an additional weighting of those high emission scenarios that I mentioned earlier. But you see for the 2030s, that range would be 6 to 13 inches. And then by 2100, basically count on 2 feet as a rough kind of minimum. Again, there's uncertainty with these numbers. I'm not saying that it's impossible that we get less than 25 inches. I'm saying that's a plausible lower bound for planning, arguably. Just as 65 inches, a little over 5 feet, can't be ruled out by any means as an upper bound, in our opinion, right? There's obviously scientific debate about some of these things. And you note the uncertainty kind of grows as you get further out in the century. And one thing the NPCC and NYSERDA did this time around was go beyond 2100 in a quantitative way, consistent with the IPCC. And here again, you see those uncertainty bounds really increase. I hope it's obvious to everyone that that's total false precision. When you see 177 inches for 2150, that is a scenario. It's a possible outcome that can't be ruled out. And then if you're thinking about the sort of total fail-safe systems, things that you couldn't afford to have fail, you might want to think about those if there's some adaptation decision that's that far out that it already makes sense to think about over 100 years from now. Okay, so now let's talk about the key takeaways for temperature. So as we've seen those average temperatures rise, we have seen the days with very low temperatures below freezing or below 0 Fahrenheit for that matter have been steadily decreasing, including some shocking numbers. I don't know if folks have seen the numbers for 2023. Just how few cold air events there were. If it was just 1 year, we could call it a blip, but of course, it's not your perception. This is part of a very rapid trend that we've seen. If I'm not mistaken, I think New York City may have only had one day in 2023 in which the maximum temperature failed to reach 32 degrees Fahrenheit. I'm not exactly sure what weather station that was based on, and don't quote me on it. But the long-term sort of climatology for mid-January would be a high temperature of around 37, 38 degrees or so. So really shocking, the idea of a whole year when you only had 1 day when temperatures failed to reach 32 Fahrenheit on the maximum side. This first bullet is referring to minimum temperatures not falling below freezing. And then, sort of other side of the coin, we're seeing a lot more of these hot days, right? Everybody knows it, days above 90, days above 95. And the fact that nighttime temperatures in summer have been warming especially much more than those daytime Tmaxes helps make it easier for there to be these long duration heat waves that are so devastating, that have outsized impacts, right? Because we're not getting that cooling off at night. So it's not just more hot days, it's these longer duration heat waves. And we know that heat waves pose a variety of greater risks, whether to human health or the risk of blackouts and power failures. One thing that under Luis's leadership, this latest report really does well is get in, and the prior version from NPCC, getting into the role of local urbanization patterns, right? When we look at extreme temperatures, not all neighborhoods are the same by any means, due to a range of factors: proximity to sea breezes, amount of shade, just to name a couple of things that can lead to large differences, including among vulnerable populations in terms of exposure to extreme heat. And Luis is going to talk a little bit later about some of the future directions, but one of the really important ones is that last bullet here about more work being needed on the impact of climate on the intra-urban heat variability and inequalities in heat exposure. Just as climate change doesn't have the same signal everywhere, it's possible that as we warm the climate, different neighborhoods will warm different amounts, in addition to the fact that they have different temperatures to begin with. So that's one of the big research areas. Sea breezes, for example, could change in ways that lead to some neighborhoods warming more or less than others, having different changes in their heat waves as a couple examples. Okay, next slide, just to show quickly the historical trends. As I sort of mentioned earlier, now this is just your annual average temperature, right? Taking all the daily maximum and minimum temperatures, lumping it all together, one number per year, which is the sort of average temperature. And you can see the individual dots, 5 different weather stations throughout our region. A lot of people focus on Central Park, for better or worse. So obviously the thick line is your smooth long-term trend. And then your circles are the individual years, right? So it's the same old story that you see with so many variables, always that year-to-year variability. But if you look, over the last 20, 30 years or so, it's, for some of these stations, we're approaching a point where sort of, even a sort of cool year today, if you will, would have been a warm year. At various points in the historical record. That might come through sort of most clearly if you look at Newark with its long record going back to 1900. But you can also see that to some extent with Central Park. Okay, and that trend statistically significant at all 5 of the stations, that upward trend. Okay, let's go to the next slide just to now show a little bit of the projections. So basically, here's the temperature and precipitation together by decade, temperature in that middle column, and the changes in precipitation, the percentage changes in precipitation shown in the right column. So if you remember that slide a few ago where we showed the 10th percentile, 25th, 75th, and 90th. So the way that translates here is, let's take the 2030s with mean annual temperature. You see that 2 degrees Fahrenheit, that's the 10th percentile. So that's kind of, roughly what we think. It's pretty unlikely that you'd see less than 2 degrees Fahrenheit of warming in the 2030s relative to that baseline period of 1980 to 2010. And then we see in parentheses is that 25th to 75th percent, roughly the sort of middle half or central range, if you will, of our projections. And then the 4.7 degrees for 2030's mean annual temperature, what we think is sort of an upper bound, for just how hot it could be. So, kind of similar patterns to what you saw before. Let's just quickly sort of unpack a little bit about the precipitation. So, you see that there's a range, and these are percentage changes. But basically, the guidance is when we're talking about annual precipitation, we think it's pretty unlikely, based on climate models at least, that we'd have decades in the future where we'd see lower precipitation than the kind of typical iconic 30-year average of 1981 to 2010. And as we get further out in the century, the odds go up that we get a decade or a 20 or a 30-year period with really a lot more precipitation than we had in the past. Look, for example, for the 2100 time frame, where we can't rule out the idea of a 30% increase in precipitation. Now, precipitation is, even in the sort of annual or 30-year average is notably fickle. There's a lot of year-to-year variability. There are decadal cycles we don't fully understand. And more importantly, this is not a strength of climate models, to be totally honest. So they have value, but these quantitative projections need to be taken with a grain of salt. That said, you see this kind of consistency. And from a planning perspective, you wouldn't want to rule out the possibility of strong droughts in the future. Maybe there's a slight chance, unlikely, but a slight chance total precipitation would go down. But from a planning perspective, in the annual average, balance of evidence suggests more total precipitation, and we can't rule out the idea by late this century that it could be significantly more. Now, we don't have time to get into all the impacts. Franco's going to go into much more depth, sort of unpacking precipitation and flooding. But just to sort of quickly note, with higher temperatures, we could also see a lot more evaporation and a lot more potential for drying out. So you can't just assume the annual average precipitation going up 5, 10, 15% will necessarily mean a much more verdant and water abundant city and region. It's going to depend to some extent on how much push-pull there is between higher air temperatures potentially sucking more moisture out of the ground and out of our reservoirs. But this is sort of what the balance of evidence suggests for long-term precipitation, annual precipitation. Franco's going to give us much more detail about some of the time scales that are arguably more important in the second part of the seminar today. Okay, let's go to the next slide and talk about some of the key takeaways on precipitation, some of which I think I've already alluded to. There is enormous year-to-year variability in precipitation. But if you start to average across 10, 30 years, the kind of trends I just showed become more meaningful. But if you're just talking about comparing one year to the next, we expect variability to continue to be the story. And we didn't have time to show it here, but to some extent, models do suggest increased frequency in extreme precipitation events. So that worst day, that worst hour, think of some of the devastating experiences that we're all too familiar with. Ida, just to name one, some of the rain from this past summer too. So while climate models do suggest that those precipitation events are becoming more frequent and more intense, I think that's not the big story. The big story is that, arguably the models might be missing an observed uptick around the world in these really extreme hours and days of rain. Although, as we may hear from Franco, if you just were to sort of hone in on New York and the cities of the Northeast, it might not be so easy to see that global trend towards more extreme precipitation events of these sort of short and devastating duration, such as we've experienced a few tragic examples of recently. Okay, let's go to the next slide, just to sort of quickly compare the previous projections of record. And again, I want to caution about false precision. I want to caution about anybody sort of concluding that these are better projections than the 2015 projections. I think anyone who's sort of left with that conclusion, in my mind, would be sort of missing the overall takeaway. These are sort of best estimates of highly uncertain fields. The 2015 projections had value. These projections have value, but we can't rule out the idea of some outcomes even outside of these projections, especially in a world where we're all sort of watching climate change happening faster than just about anybody or any climate models predicted. That said, your two rows here are annual average temperature and annual precipitation. So what you're seeing first in that sort of white row, NPCC 2015, the actual projections for temperature in that top row from 2015. And then below that, in that bluish color, the departure or how different our current projections are from 2015, right? So how much these new projections move the needle and in what direction. So you can see, for example, if we were talking about the temperature middle range, that 25th to 75th percentile, it's getting slightly wider in these new projections. We're saying that at the lower end, we think that it could be we're now saying 4 degrees is a lower bound, whereas we said 4.1 before. And at the upper bound, we're now saying we can't rule out 6 degrees, 5.7 plus 0.3, whereas before we said 5.7. But we're deeply into the realm of false precision here. Don't focus on these exact numbers. But that's the way to interpret the graph. And then for the percentages, so if we look at the 2015, sort of the third row, that NPCC 2015, that was the projected in 2015's assessment changes in precipitation. And then what you see for the latest projections is basically incrementally how much you'd add to that. So just give one example, the 2050's high-end annual precipitation, the estimate had been a 13% increase for the 2050s. In the 2015 assessment, where you see a +1, interpret that to mean now we're saying 14%. 13% plus 1, 13 plus 1 instead of the 13% before. That's the way to interpret that. So I think, certainly to my mind, the important takeaway here would be don't think of the new projections as producing any real significant differences for annual precipitation relative to what the NPCC 2015 said. If anything, this is sort of pretty consistent with the projection, given the inherent uncertainties that I've now alluded to too many times. But it's just a critically important point. Okay, so I think with that, let me turn it over to Luis, who will give us more context and really sort of deeper situating of the projections I just described in the sort of evolving and deep NPCC work. Thank you. Back to you, Luis.
Thank you, Radley. So we have evaluated a lot of the state of the science historically as far as the NPCC sustained assessment and updating of these projections of record that Radley just sort of gave us a really nice run through of. But we are aware that we still have some knowledge gaps, which in turn sort of give us avenues of where to direct our research efforts in the future as we move to future assessments of the climate of New York City. On the topic of sea level rise and storm surges, we have limitations in our observations and limitations in the models that we have available. I'll remind that a lot of the model information we're sort of relying on is global, and due to computational limitations, are relatively coarse in resolution or in the level of detail they can resolve around many of these impacts. So we might see that as we improve our models, we improve our computational capability, and improve how physics of sea level rise and various storm surge events are represented. We may be able to get a better sense on how the flooding events associated to these two types of extremes might be represented or inform our knowledge of the spatial extent, the intensity, the height or depth of these types of events. On temperature, there's still a lot to do. One of the biggest, the same limitations that we have on the spacing and or the spatial resolution exists for temperature. We have some additional constraints there in that the city itself adds a lot of physical processes that you would not really see in other types of land cover. Thinking about the effect of built surfaces, the various building materials we use for buildings, for roads, etc. The geometry of the city itself, which can add heat storage. If we have a lot of additional volume, additional mass of buildings and other built-up structures, that means that we can hold on, intercept and hold on to a lot more of that radiation from the sun, and lead to additional, we call urban heat island effects, where the city might be a little warmer in parts compared to outside of the city, or even compared to other parts of the city. The effect of technology and adaptations like air conditioning, which is essentially taking that heat stored in buildings and moving it outside into the ambient air. And we have to add more heat to the system and more moisture into the system, which might in turn affect our thermal comfort, and affect the rates at which people are affected by extreme heat. And these are all sort of processes that are either poorly or not really represented in the large models. So we are sort of left to run case studies or simulations with very limited time series. Certainly very difficult to run 30-year time slices due to the computational constraints that these additional processes and the additional resolution we need to run them. So we kind of at this point left over running these limited scenarios, and we actually did an exercise on this in the previous NPCC, and showed what some of these projections and the spatial distribution of some of these temperatures might look like. There's also this other aspect of temperature that we have not really looked at, and we have poorly explored its relationship with the overall changing climate, which is how do indoor temperature and more broadly thermal comfort and thermal extremes might be changing as a function of a warming climate. We first of all barely monitor this information, so we might not even have a sense of what different parts of the city and even different floor heights and different distances from the roof and different types of buildings and materials might affect this. So there's a lot of science that we still need to do to uncover some of these impacts and better understand some of these processes, so that we can then perhaps develop projections for them. There are also some uncertainties around some of the extreme events that may help or contribute to the stabilization of ice sheets. That's more of at the very large scale, and that might not be fully represented in some of the modeling that we have included. On the precipitation side, modeling extreme events that happen at hourly or even sub-daily scales really remains a challenge. One, because getting information from these projections from the global models might still remains challenging. It's a lot of data and storage constraints. And on top of that, some of these processes that lead to some of these types of storms themselves might not be very well represented in some of these global models. And then finally, there's this piece on how the risk of drought might be changing, and that's more of a regional question rather than just a New York City question. But of course, it has very deep implications for the city itself, given that it's a big source of that large water demand. So there's still a lot of work to be done to, one, see how drought might be changing, how the periods without any rainfall might be changing over time, but also how that demand for water might be changing in the city itself. And looking at these two at the same time to see how we might how our needs versus our supply of water might be changing as a function of that climate signal and as a function of how the city itself is changing. Next slide. So where can we find these projections? We are right now in the process of rolling out 2 chapters or 2 reports for the 4th New York City Panel on Climate Change around the climate science working group's work. We have a special report that outlines the projections of record that Radley just gave us a review of, going into a little bit more detail, not just on the annual mean changes, but also into some of the extremes like hot days and even cold days and extreme precipitation days. And then we will have a follow-up or a full report that goes into our understanding of the climate science around topics like extremes, compounds, compound risks, and even a little bit on the spatial distribution of temperatures in the city. Right now, it's sort of finishing its review process from the city and from the scientific peer cohort, and should be coming out in April 2024. Next slide. So a few questions that perhaps we can think through together as a group. We just given all this sort of a bulk of information and sort of this review of the New York City panel's climate changes work is sort of on this work that you or your team does. Are there similar climate projections under discussion? Is there something in the pipeline that you know of, or is there already something similar to this being developed by your location or your region? If you do have them, how can we integrate these types of projections into decision making, into different various kinds of investments? And if there are some challenges to do that, what would be some ways of overcoming them? What some of policies or various types of data can we provide, or people like us provide to sort of help put this data into action? So, and I think the next general discussion. So, thank you.
Thanks so much, Luis and Radley. That was really great. We have about 8 minutes or so for Q&A. So I invite folks who have not, there's a few questions that are already in the Q&A box, but if you have a question you'd like to pose to either of the speakers, please do so, and we'll try to get to it now, or if there's not enough time, we'll get to a general discussion at the end. So Lewis is asking if, how you get this message out. Is there a public education campaign associated with doing these projections? I mean, obviously this event is one way of trying to get the information out, but I don't know if you want to talk either of you want to talk about other ways that you have been trying to get people to be aware of this work.
Luis, do you want to say anything? Yeah, you want to say anything about the current approaches?
Yes. No, that's a great question. So as you said, Franco, sharing some of the results even early as we're doing now in this type of event or in this type of forum is one of those approaches. And we have had the various working groups sort of develop their own sort of external engagement strategies depending on the type of work that they're doing. Some of the working groups are working with community groups and other types of stakeholders. The city, the MPCC working group itself shares this information with the city periodically, and the city actually reviews this information as part of that education piece. And then I believe we've been in discussion to have various levels of or various types of dissemination strategies on top of just the report itself, which is it's very much sort of an almost an academic document. So having different sort of channels of distribution for that, either through websites or other types of online or digital engagements is something that we've been discussing. Radley, I don't know if you had any other details around that from your experience.
No, I think that's great. I mean, definitely, I think it's, sort of like the question of how to deal with climate change. It's like every possible way, right? It takes all the above. It takes communicating, including with those maybe who, might be oppositional to some aspects, to the extent that there's still some folks like that in our region, which there are. But then especially, getting the message out to some of our most vulnerable communities, finding ways, for example, to connect with people who maybe English isn't a first language. Not that those are necessarily correlated with other types of vulnerability, but just, doing all we can to, whether it's, one end of the spectrum, sort of financial firms, in a different sense, it might be, really vulnerable communities that have contributed almost nothing to climate change. Getting the message out, even if it's to individually, to sort of small groups, is so important, especially for those who haven't been exposed to this information as much, or who haven't had it presented to them in ways that really resonate with the vulnerabilities they face.
Great, thanks. Shifting gears a little bit, Vivian is asking a question about some of the literature that suggests that SSP 5 8.5 gives you more of a signal in your projections than the SSP 2 4.5. And I don't know, maybe you want to, if you're aware of that that sort of set of thoughts, what they're alluding to exactly.
Yeah, so I think this was, I'm guessing, Vivian, that I probably expressed myself in sort of a clunky way. All I was really trying to say is that while SSP 5 8.5 probably will have unrealistically high emissions, I think most experts would suggest that's the case for 2100, although again, we can't totally rule out the possibility of emissions that high. The only point I was trying to make is that I think there's growing evidence that for the emissions that we've seen to date, for example, climate models may have underestimated, when looking at extreme events, for example, they're not sensitive enough, basically. So I was just sort of simply making the case that by crudely turning up the dial, and I think there's no disputing the fact that, in order to get a bigger signal from climate models for temperature increase, for changes in precipitation, you got to turn the dial up higher, essentially, right? I mean, that's sort of just sort of the basics of it. So I think the point I was trying to add, and probably did so in a clunky way, was sort of, we might be right for the wrong reasons if we artificially inflate emissions higher to partially make up for the fact that I'm more and more convinced that climate models aren't sensitive enough to greenhouse gases, just as impact models aren't sensitive enough to greenhouse gases. So turning up the dial is a crude way to sort of partially sample that right tail. That's what I was describing.
Right. So two questions here that are kind of, I think, trying to get at similar points, trying to pull away the veil a little bit from these changes in mean values. And so one of the questions is really about hot days and whether the changes in the mean may have to do with hot days extending later into the fall than previously. And then, a similar question is about the precipitation increases, whether they're attributed to some particular seasonal signal or some very large events that then collectively, represent a big part of the annual total.
Yeah, so I can I'll take a quick stab at these. I think I'm not sure if I'm not seeing part of Lewis's question or if it just cut off at the end, but yeah, I mean, that's absolutely right. It's not just in the middle of summer having hotter days, it's the shoulder seasons, right? And there's, more and more research. Maybe some people have been following, this our summer, the recent Southern Hemisphere winter, in a variety of places had a lot of heat wave days, be it Brazil, some parts of Southern Africa. So yeah, it's definitely not just the hardest summer. It's higher temperatures in the hardest summer, but also if you think of this shoulders and expanding the season, it's not just at the far end, it's also, hot days earlier, right? I think, didn't we, I'm not sure, I don't think the city did, but certainly where I am in the Hudson Valley, I think we hit 90 multiple times in April, if I remember right, in 2023. And then on the second point, this is a really good question, and I wish I had a better answer for you for New York. My intuition is that we can't entirely attribute all of this increase in annual precipitation to a couple big storms. Most years aren't going to have that hurricane, for example. But a disproportionate amount of it, I think, is in these really strong hourly. So I think you have to look across the whole distribution, including your sort of run-of-the-mill winter storms, even if it's not a big beast of a storm, warm the atmosphere a little bit, warm the surrounding ocean, and you're setting the stage for a little more rainfall falling. So you can't say that all of the increase in annual precipitation is coming from a few huge events. But I think, and again, we need to look at the New York City data, but certainly for the mid-latitudes as a whole, it's fair to say that the rare extreme events are disproportionately are hitting beyond their pay grade in terms of increasing the total precip, but you can't attribute all of it to them. For New York City specifically, have to go to Art or Franco, probably for something like Art DiGaetano or Franco for better answers. But those rare events are disproportionately important, but not the whole story, I would say.
Yeah. So maybe we'll just take two more quick ones. One is if you've correlated any of these changes in climate with changes in, sort of operational costs in the city. And I know that may not be, this may be something that we'll cover in a future workshop, but just if either of you had any high-level thoughts on that. And then the second was whether the Antarctic rapid ice melt scenario is factored into any of these climate model projections that you looked at.
I can take a stab at the first question, and maybe Radley can look at the second one. I'm not sure we've had a formal exercise, right, on looking at investments, and maybe Radley or even Dan or Franco might have a better answer than that for this particular NPCC report. But the understanding is for a lot of these investments, you're always looking at what is the cost of no action, right? Given what we know about the projections, and a lot of the how these investments are decided is, and even at the federal level, when you're looking at some of the funding from the federal government, that's a necessary exercise to justify any kind of investment being done. Now, whether that's panned out or not, it's something I think it's a little bit of an open question. I recently even saw a talk from the city's Department of Transportation, and just looking at how difficult it was to even quantify the cost of Hurricane Sandy back when it came in terms of loss of business, loss of infrastructure, and all other kinds of costs. And that was something that even when I saw this talk a couple of years ago, there was still kind of wrangling, about a decade later. So it's not a straightforward exercise to quantify even sort of the overall costs incurred by these sort of extreme events, and especially when we're talking about avoided risks. It's a little bit of a difficult question, but I think it's something worth exploring in terms of historical investments. And I'll let Radley take the question about the ice sheets.
Great, and I'll be real quick so we don't cut further into Franco's time. We didn't do an updated ARIM or Antarctic scenario for these projections, but again, just to sort of highlight, I don't see the 22 projections as sort of better, than other assessments. So my personal opinion would be that the ARIM, was valuable when it was created several years ago, and that it remains valuable today. So I would encourage, especially for that thing about low probability, high consequence outcomes, planners keeping it in their sort of range of contingencies that they're thinking about.
All right, well, thanks to both of you, and sorry to those who have submitted questions that we haven't been able to get to. As we move on to the next portion of the presentation, maybe Luis and Radley might want to the extent possible, type some answers to some of those questions that are still in there, and if not, we can get back to them at the end of the next part of the presentation. So with that, I'll take us into the realm of flood risk in New York City, and I'm very excited to talk about this. Previous NPCC teams have talked about flooding, of course, but there has never been a dedicated sort of report, an NPCC report focused on flooding. And so my co-chair on this, Bernice Rosenzweig from Sarah Lawrence, and myself and a very large team that includes some folks who are actually on the call today. I see Phil Orton, Nicole Mayer, Timon McPherson, but we have a number of others who represent NGOs, government, academia, and private sectors who all sort of put their heads together to produce this 65 plus page report to talk about flooding in New York City and assess to the best of our ability what's known about flooding and what some of the challenges are. And so what we'll do in this presentation is just sort of highlight some of that work. We'll talk a little bit to start off about flood risk, flood vulnerability, and flood hazards, just to get some of the terminology that can be quite confusing out there, and then go through some of the research and some of the key messages in this section of NPCC, and then again, like we did with the first presentation, lead up to some discussion and questions at the end. So the flood risk is really determined by three things, right? It's the flood hazard. So what is it that happens that causes the flood? What is the magnitude of that hazard? How big is it? And how frequently does it occur? But then once the hazard occurs, you really need to focus on the exposure, right? So you can have a lot of water flooding a wetland, and that doesn't necessarily impact people. But in an urban environment, of course, exposure to the hazard is of concern. And it's not just the exposure of people, property, and infrastructure, but what we've tried to do in this flooding report is to also talk about the impacts of flooding on natural and nature-based infrastructure, ecosystems, because of the role that they play in quality of life and other services in the city. So you've got the hazard, you've got the exposure, and then you've got a variety of attributes of the exposed population or the exposed ecosystem that determine how well it's able to withstand that hazard. And those could be social factors, ecological factors, infrastructure questions, technological factors, et cetera, that all kind of contribute to flood vulnerability, which we decided to define or adapt based on previous definitions in this chapter of as the characteristics of an individual, community, or an ecosystem that influences its capacity to anticipate, cope with, resist, recover from the adverse effects of one of these hazards, of a physical event. So we're interested in the vulnerability, and there are, of course, people who are vulnerable to flooding. And in New York City, as we've seen repeatedly now through some recent events, residents of 1- and 2-story unit residential buildings and residents of subgrade basements are among those who are most vulnerable, as well as individuals who have other attributes that make them more socially vulnerable to a variety of risks. So the elderly, disabled, low-income groups, groups that have been victims to racism and marginalization of different sorts in the past. And that really is also a unique focus of this NPCC report is the focus on, of course, previous reports have focused on equity, but we all started this process really trying to center equity in our work. And Tommy McPherson, who's on the call now, and colleagues have been developing a flood vulnerability index that can be used or superimposed on top of hazard exposure areas to determine the level of vulnerability. And you can see here on the right, some of the properties of that, some of the variables that go into that flood vulnerability index. And this is a really exciting advance now that we're able to sort of overlay exposure and vulnerability and identify specifically vulnerable populations. But of course, it's not just people, as I mentioned earlier. Ecosystems are vulnerable to flooding as well. And so, as the sea level rises, as the water advances over the coast, and if the coast is characterized by wetlands and the land side of those wetlands abuts to a road or a building, there's limited space for that wetland to advance landward as it has done historically. And so you can see wetlands drowning. A storm surge, for example, can bring in the case of New York City, saline water and apply that saline water to a landscape, a vegetated landscape, with different types of impacts on the vegetation that is there, whether it's native vegetation that's been planted there. As the sea level is rising, the water tables are rising, salt water is intruding not just on the surface as a result of storm surges, but underground through the aquifers, and that also is having impacts, salinization. Waves, high velocity water, both contribute to erosion and have impacts. Changes in the hydro period. So the hydro period is defined as the frequency of flooding. And so, for example, some of the tidal wetlands that you have along the coast in New York City depend on a certain frequency of flooding. If you don't get a certain level of flooding because of evapotranspiration processes and drainage processes, those systems will dry out, and they may dry out such that the plants suffer desiccation and can't withstand that particular period of time. And so that can result in changes in species distributions. And so all of that, we know that natural systems provide a variety of different ecosystem services. And what we really wanted to do in this particular chapter is to call out not just the vulnerability of people to flooding, but the vulnerability of a lot of the natural and nature-based systems in the city to flooding themselves. Because if they're impacted, then we have less natural flood protection from those systems. So there's a variety of sort of determinants, when we talk about the magnitude of the flood hazard. The sort of simple ones that you might think about are the depth of inundation, right? Of course, the higher the depth of inundation, there are some really nice equations that are used by various government agencies to associate depth with damage. But a depth of water, if you have several feet of water impinging itself against the foundation, that load can cause the foundation of a building to cave in. Of course, the deeper the water, the greater the buoyant force on something like a vehicle, which can float and move and crash into other things. So of course, the depth of inundation matters, but we also care about the duration of inundation. So the longer that an area is flooded, the greater the loss of service or access. So think about transport, for example. If the road is flooded for an hour, it's very different than if the road is flooded for several hours. So the duration of flooding as well as the depth. But there's also the rise time, and we hear a lot about flash flooding, which is defined as rise times when the water comes up in less than 6 hours. And that can often leave people unprepared. So we may not know that this is coming, and it may not be enough time to move our vehicles, get out of the way. And so rise time is important as well. Velocity, so moving water as we all know, can knock people down. It can cause erosion. It can undermine foundations. Fast-moving water, which is associated with a rapid rise time, can be problematic. I've sort of alluded to waves, the run-up and slam of waves. Water chemistry, and I talked a little bit about salt and the corrosion of salt, but you know, when there's a flood, the flood waters are conveying pollutants, bacteria, toxic materials, and that has a variety of health as well as ecological implications. And then finally, live electrical current. You know, as we know, that water is a conductor, and electrocution associated with downed power lines actually hit College Point, Queens in 2004. There was a death there. So, you know, a flood, there's lots of different ways to talk about the magnitude of the flood hazard. And this graphic over here comes from the Bronx River and just shows a particular, during the Ida event back in 2021, you can see, you know, here are the different stages that correspond to historical flood stage. And you can say not only was this a high, you know, above the major flood stage, it stayed there for a period of greater than a day. There was a very rapid rise, and you know, you can imagine the implications of that, and we know the implications of that. So another key message here is just to point out that there are 4 principal types of flooding hazards in New York City, right? So we're often used to thinking about flooding or just using the word flooding kind of flippantly, but a pluvial flood is different from a fluvial flood. Excuse me, it's different than a coastal flood or a groundwater flood. And I'm going to show an image in a moment that sort of depicts what those look like. But it's important to point out that each one of these has a very unique and changing geography of exposure. And those geographies of exposure will likely expand in the future due to climate change. So let's talk a little bit about those individual flood hazard types. So pluvial flooding, which is shown in the upper left, occurs when the rate at which water or rainfall occurs exceeds the capacity of the landscape, if it's a pervious landscape, or of a drainage system, if it's an urbanized landscape, to receive and drain that water away. So if water is falling out of the sky at a very high intensity and it can't get into the ground, it ponds instantaneously on the surface, and that's what we call a pluvial flood. And that's very different from a fluvial flood, which is the upper right, which is then if that water, you know, after it's pooled on the landscape, starts moving in the direction of the topographic gradient and gets into a stream or a river and starts moving downstream and gradually concentrates greater and greater amounts at the downstream end of that water, of that watershed, you get a fluvial flood. So a fluvial flood is caused when a creek or a river exceeds its bank full elevation. In other words, the level at which the water naturally flows through the creek and doesn't overflow into surrounding areas. And especially if we've developed, as we have in many cities, we've put buildings and infrastructure and other things in the floodplain. So in the areas immediately adjacent to the river, if we've done that, then this exceedance of the bank full capacity of the river or creek causes a fluvial flood. Those two floods are very different from a coastal flood, which occurs when we have an extremely high tide, a storm surge, excuse me, or as Radley has mentioned, you know, even just a regular high tide in the future, as the base or the average sea level creeps up over time, a regular high tide could cause water to start to go over the landscape in the coastal areas and coastal plains. And so coastal floods come from the coast and are different than from a pluvial or a fluvial flooding event. So you can have a coastal flood when you don't have much rain, and you can have a pluvial event when you don't have a very high tide. And then, of course, there's groundwater flooding, which occurs when the water table starts to creep upwards to the point where it starts to flood basements, infiltrate into storm drains, make the surface soils soggy and waterlogged. And, you know, in parts of New York City, parts of Queens and Brooklyn, that for decades were actually dewatered due to municipal pumping of groundwater. And then subsequently those areas developed with artificially depressed water tables when, because of reasons of contamination of groundwater and other purposes, excuse me, other reasons, that groundwater pumping ceased, the water table crept up, which led to large areas of exposed groundwater flooding. Excuse me. And as sea level is rising, this is causing an increase in groundwater flooding. Wish I had a glass of water. Compound flooding is the co-occurrence of multiple flood hazards. And so, for example, if you have a tropical cyclone that causes heavy rain and storm surge to occur simultaneously, you can have the combination of a coastal and a pluvial flood event. And one of the key messages is that, excuse me, I'm going to have to get a glass of water in a moment, is that the heavy rain and storm surges don't actually very frequently co-occur. But when there is a tropical cyclone, there's a non-zero probability that you will get, within a certain period of time, which is critical, you could have heavy rain and a storm surge. And that's the most common compound flood hazard that, that we have in New York City. Of course, you could also have intense rain that occurs, for example, in the spring when water tables tend to be higher, and then you have a combination of groundwater flooding and pluvial flooding. Just one quick second while I get a glass of water on my, it'll take me 10 seconds. Apologies for that. And an example of this was actual tropical storm Irene back in 2011, where we had a 4.2 foot surge at the Battery with heavy rainfall across the region. So climate change can also exacerbate compound flood risks. So this graphic produced by our team shows what happens when you have sea level rise on the left in combination with sea level rise in a coastal region that has already high water tables. And you can see, under sort of ideal conditions, you would have a water table that kind of goes back and is slightly higher than mean sea level. And as that mean sea level goes up, there's an associated increase in the water table, which could reach, as you see over in the right here, some underground pipes where you can have what's known by engineers as I&I, inflow and infiltration into those pipes, because pipes tend to be leaky, or you can have flooding of depressed areas, for example, a park, where you now have flooding where you previously didn't. So another key message here is that, of course, the factors that Radley and Luis talked about will increase flood risk. So changes to the frequency and the amount of precipitation, rising sea levels, the occurrence of tropical, post-tropical, and extratropical cyclones, nor'easters, for example, will increase these flood risk factors. One of the things that I think Radley alluded to is that we've got good data on annual precipitation, on daily precipitation, but some of these flooding events that we're talking about, in particular the pluvial flooding events, when you have these intense downpours, or sometimes known as cloudbursts, you can have a really intense pulse of precipitation in minutes. And it only takes a few minutes. If that water is coming down faster than it can go into the ground, it immediately ponds in the street. And so high or sort of short duration precipitation data, one of the challenges that we have is that data is not available. We only have about 20 years of that data in the New York City region. So it's really difficult to discern trends in this sort of short duration, high intensity precipitation that is among the most problematic when it comes to pluvial flooding. But nonetheless, our perception is that those events are increasing at least in frequency. And some of the research that we've done has sort of looked at that over the last few decades, there's been an increase in the frequency of these really intense events, though we're having discerning a trend is difficult in the actual intensities because of the fact that we just don't have that high resolution data for a long enough period of time. But flood risk is also increased by other things. So, and we know about this, urbanization leads to an increase in impervious surfaces. Landfilling has done things like helped us lose more than 90% of our wetlands in the city of New York. Dredging by deepening channels, in many cases to promote shipping. We reduce bottom friction and we can increase water flow. And of course, depending on how you do that, you might be encouraging water to drain away for an area where there's flooding, but you could also be encouraging flooding by allowing more water to come into a place. I already mentioned these changes in groundwater extraction rates, and all of those types of changes have impact, as I said in the very beginning of the presentation, have gradually impacted our natural and nature-based systems, which themselves provided some flood mitigation. So it's kind of a vicious circle where the flooding impacts the nature-based systems, and then the nature-based systems are less capable of providing the protection against the flooding. With the courtesy of Eric Sanderson and Lucinda Wright of New York Botanical Garden, put this graphic into the report, which is a really interesting graphic. On the left shows in green the historical wetlands of the city, and in blue the historical streams. In the middle panel shows the 100-year special flood hazard area. Some of you think of that as the fluvial or coastal 100-year base flood elevation. You can see, a real overlap in the areas that were historical intertidal marshes and the areas that today are within the 100-year floodplain. And over on the right are some graphics produced by New York City DEP through an academic team and a consultant team that includes some folks who are on the call today. Timon McPherson was part of that effort, as well as Arcadis. That actually, for the first time ever, started to map out pluvial flood risks in New York City. And so what this particular scenario that's shown here is the extreme stormwater flood. So this is 3 inches of rain in 1 hour, but if it occurred in 2080 with 58 inches of sea level rise. And you can start to see those little blue channels there, that many of them have to do with low points in streets. But if you compare that to the panel on the left, you can also see the sort of relationship with the historical creeks that existed in the city. And so there's this historical legacy of urbanization that is a big part of what we're dealing with on flooding. So the geography of flood risk in New York City, the pluvial flood risks are present throughout the city. And that's, I think, a really interesting statement. Some may find surprising, because we're so used to thinking about the special flood hazard areas, the sort of FEMA floodplains, which are located along the coast and along rivers. But as I just showed in that graphic to the right, pluvial flood risks occur everywhere. It could happen if you have a cloudburst at some point anywhere in the city. That rain is falling down. If it's hitting impervious surfaces, it can't go into the ground. It goes down to the end of the block. It finds a catch basin, and it can only get into that catch basin at a certain rate. And if that runoff is generated at a rate that exceeds the capacity of that catch basin, you can get flooding anywhere in the city. And so pluvial flood risks are very difficult to plan for, also because the climate models are still not able to tell us exactly where cloudbursts will occur. So, in advance of a storm, we'll hear the National Weather Service will tell us that there's extreme precipitation. That's a possibility, but we won't necessarily know where that intense precipitation cell will be. And if it's given the uniformity of the infrastructure that we've built and the land use that we have, you could have a pluvial flood risk wherever that cloudburst happens to occur. And that's different from fluvial flood risks, which in New York City are localized in places where we still have streams like the Bronx River and Valley Stream out on the edge of Nassau County and Queens, and some smaller inland creeks in Staten Island. High tides, rising sea levels, and coastal floods are a special concern in Jamaica Bay, but along all of the coast of New York City. And then the groundwater flood risks are greatest in places in Brooklyn and Queens, where there was historically a lot of groundwater pumping and where the city subsequently developed and then the water table rose. So, I've been talking about how we need to go beyond the FEMA special flood hazard area. This graphic has a lot of information. It does have the FEMA, the 100-year event right there. But what we're seeing is that there's been recent work to try to map for other flood hazards over larger areas. And so, again, this stormwater resiliency study that came out of that the city funded back in 2021 really has advanced our ability to superimpose hazard areas exposure and vulnerability. And so, you can see here some of the types of flooding that are considered. We've got, some pluvial, some coastal. The USGS has been doing and will be doing more work on modeling groundwater estimates, groundwater levels in portions of the city. And so there's some really exciting work happening now in mapping flood hazards beyond the FEMA flood hazard areas. And just to show really quickly what the type of analysis that modeling enables, this shows NYCHA, New York City Housing Authority properties at risk to pluvial flooding. So it's just an overlay of, in this case, the moderate stormwater scenario with no sea level rise, and NYCHA parcels, and you can see the red ones would be inundated and the others would not be inundated. Or another example would be NYCHA properties at risk to groundwater flooding. And this is looking at some of the areas with less than 10 feet of water table out in Queens and Brooklyn and other places, and where the NYCHA properties are. So what do we do with all of this? Of course, the goal is to manage flood risk. And we spent in the report a significant amount of time reviewing the latest and greatest research on how to do that. And it turns out that there are structural approaches and non-structural approaches. And so structural approaches tend to be physical or engineered systems, in some cases natural systems. So you see elevating buildings, building dikes, dams, levees, embankments, implementing active or passive barriers, pumps, valves, backflow preventers, flap gates, doing things to increase the capacity of the sewer system to pass water. I would put in this category facilities that detain or retain stormwater, and that includes the city's really growing green infrastructure program and its cloudburst program. It's work with permeable pavements, permeable turf fields, subsurface tanks. Wet and dry flood proofing of buildings is also among structural approaches. So these are, either preparing your building to receive water through a vent, for example, that allows water to come in and then eventually be pumped out without damage, or dry flood proofing, doing things to the perimeter of your building to keep water out. And there's some interesting research happening around the world in floating structures, but those are all sort of structural approaches. And then there's a variety of non-structural approaches that rely more on education, awareness building, laws, policies, knowledge buildup, and try to, a variety of things that help people to prepare for flooding. And so you could think of insurance as being in that category, or early warning systems, or advances in flood forecasting, or incentives that might encourage people to either move out of particular flood prone areas or to seek out opportunities to elevate within those communities, or move internally. Disaster preparedness essential. So what's interesting about these programs is they could be implemented by government agencies. So the city of New York could do some of these things, but some of these approaches could also be implemented by individuals, by property owners, in the context of a redevelopment project, by sort of large groups of communities who get together and try to plan. So I think the other thing that's interesting about flood risk management is that when you think of a bucket of these ideas, they kind of go, another way of categorizing them are resistance approaches. So those are approaches of saying, hey, I live here, I'm going to keep the water out. I'm going to fight as hard as possible to keep the water out so that I can continue to live here. And what I would contrast with those being a resilience approach, which is recognizing that the water is trying to come in and to developing ways to either adapt to that new normal, to the fact that there will be water in this place, or to transform and to fundamentally change the way that communities are designed and operated to be better prepared for the future. And I just have a couple more slides here, just talking a little bit about what we learned by reviewing the literature of the sort of pros and cons of these two general categories of flood risk management. So the resistance approaches can be the fastest and easiest way to provide flood protection, right? Build a dam, build a dike. But there are some negatives. One is the potential impact of those resistance approaches on natural systems, because the same water that is a problem for us in the built environment is a need to the natural environment. And so resistance approaches often prioritize flood control over natural system functioning. These systems, once we build them, can be very difficult to retrofit and adjust. And that means that, given the uncertainty that Radley and Luis were talking about earlier, it makes it hard for these systems to, if you're the designer of these systems, what exactly is the condition that you're designing for? And how do you, if you don't design for the absolute worst case scenario, what happens if you design for an interim scenario that turns out to be inadequate? How does this system not become obsolete as the future climate reveals itself? There's some interesting research out there that tries to document the possibility that these resistance strategies can create a false sense of security among folks who, the same folks who they were designed to protect. So you feel like, now I'm living behind the barrier. I don't need to get flood insurance. I don't need to do other things. I don't need to raise my utilities. And that can be a problem. And as a result, the consequences of the failure of one of these resistance approaches could be worse than without protection. With people who are living with a risk, maybe more cognizant of the potential implications of that risk and be more prepared when a hazard occurs. And so there's some interesting research that says that these resistance approaches may resist or may reduce the capacity of communities to adapt over time, because if you're flooding episodically, you're getting more and more used to the fact that there is this new normal that is occurring, and we therefore have to change and transform in some way. The last one here is that by reducing the personal experience of flooding, public understanding can become limited. And, it's related to the previous one, increasing latent risks. Excuse me. I very much apologize for this cold. Resilience strategies, on the other hand, you might say, yes, this is what we need to adapt and transform communities for the future. But implementing these resilience strategies can be complex. It requires that, to the extent that resilience strategies are decentralized, so doing lots of little things all over a flood exposed area, that requires that the individuals who make decisions in those areas have access to information and resources about flooding, and that's not always the case. Those local stakeholders need agency in decision making, and they need the ability to sort of coordinate a local effort. So are we all doing the same thing here? How are we working together? there's this interesting research that says that this sort of decentralized resilience approach may have this unintended consequence of shifting the burden of flood management from government decision makers to groups who take sort of protection in their own hands, and they may not have the ability, the resources to actually follow through and design and implement and maintain whatever it is that's built. All of this is logistically, socially, and institutionally complex, especially given the traditional roles that we have of different agencies responsible for different aspects of flood risk management, and the implication here being the types of changes that that would be necessary can be quite significant. So I think just two more slides here. The last one is just opportunities and limitations of nature-based solutions, and this is something that we called out in the chapter. All of the recent research that talks about how wetlands, for example, can reduce storm surges if you have really large expanses of wetlands, or how even small areas of wetlands can attenuate storm-driven wind waves, or how by restoring streams or daylighting streams, you can dissipate fluvial floodwaters, how vegetation canopies can prevent erosion by intercepting the kinetic energy of raindrops as they come down. And of course, green infrastructure on a local level can moderate pluvial flooding. But really the point here is that nature-based solutions, their ability to provide flood protection value in a city like New York, is highly dependent on local conditions, the scale at which they're being implemented, and how they're designed. And so over on the right-hand side here, there's a graphic that just shows each of those curves is the cumulative amount of precipitation that fell at either Central Park, JFK, or LaGuardia during Irene, Sandy, and Henri over the last few years. And this is based on some of the 1-minute data. And then those two horizontal lines are the design rainfall per the city's unified stormwater rule. If you're designing a green infrastructure practice, for example, what's the design rainfall if you're in a combined sewer district? So let's say the upper value there, which is for site connection permits, is 1.85 inches. So you can see that even if you spec designed your practice to treat 1.85 inches over the tributary drainage area of your practice, you would have not been able, with that green infrastructure practice, to reduce the pluvial flooding associated with many of these extreme events, Sandy notwithstanding. So there are some real interesting ways that we can start thinking about how to utilize and how to scale nature-based solutions, and how to redesign nature-based solutions so that they can not only provide the water quality benefits that we often attribute with them, or the public amenity benefits that we commonly expect of them, but that how they can also sort of provide a benefit in the context of flooding. So last slide here, there's no singular approach to equitable flood risk management that's applicable in all neighborhoods. We need a comprehensive approach for each exposed community. It's probably going to include a combination of structural and non-structural measures, including nature-based solutions. The goal is really to empower community stakeholders so that the process of building flood resilience is also reducing social vulnerability, advancing equity, and addressing, hopefully, some of the other needs and values and goals that those communities have for themselves. So knowledge gaps, these are the ones that are listed in the very end of our report. We need more monitoring, modeling, and mapping of flood hazards and their interactions, especially in the context of compound flooding. Especially important, as I mentioned, sub-hourly precipitation data, stream stage data, and groundwater data. That's all going to be critical. Using things like the Flood Vulnerability Index to advance equitable flood risk management. Advances in, we're sort of granting decision-making power, developing new sort of local governance strategies whereby non-governmental stakeholders can participate in the development or the conceptualization of neighborhood scale flood risk management. And then finally, developing incentives, policies, and other things that can really foster the long-term transformation that we need to address this risk. So with that, we have a few questions here on, are these the types of flood hazards that are under discussion in the communities that you work in? Do you have other thoughts on how to address these different types of flooding, and other thoughts you might have on what's required to do so? So with that, I'll open it up for discussion. So I'm looking in the Q&A, and maybe what I'll do is, since I'm not seeing any specific questions on flooding, will you looking into the capacity of New York City sewer system to handle future flooding? So in our chapter, we actually do provide some recent research that was funded by New York City DEP that talks about, from analysis of catch basins and stormwater curb cuts into green infrastructure practices, the capacity of various drainage system elements in their ability to intercept runoff on the street. And so we'll have some information on that in this chapter. Maybe we'll go on to Julia. I don't know if Radley and Luis are still here.
I'm here.
Okay, great. So Julia's asking, this is a more general question back to the first part of the presentation. How does NPCC see these projections informing other cities and communities in the region? So they're specific to New York City, but what efforts are there to sort of contrast these results to other efforts? And she's talking about IPCC, NOAA, NASA interagency sea level rise report, so that end users regionally can understand the differences and similarities between these.
That's a great question. And I'll add sort of like an additional wrinkle here that for entities that either have infrastructure or assets that cross some of these boundaries of the city, this is an existing challenge in NPCC, and using NPCC projections, sort of like the Port Authority and even the MTA may see challenges around this if they only have sort of partial coverage of their boundaries. More directly to your question, I think there's limitations in sort of like a very local focused assessment like we're doing here in NPCC. There's a lot of work that may not be directly transferable to some of the communities around us, in spite of having very close proximity. While there are some of the other work that might be very much transferable, and we even use some of the information from nearby communities in our historical assessment. We look at temperature records from stations in New Jersey that are relatively close to the city. And one caveat here is a lot of the information we do use for the projections of record, especially for those in temperature and precipitation, come from these global models. And the grid spacing or the spatial detail in those models is often in the order of 100 kilometers or 50 kilometers for some of the models. So even though we're sort of tailoring some of these projections for New York City, we could sort of transfer this approach and use our techniques in other locations. And at the same time, some of these variables might not change very much, going from place to place, from the point of view of these global models. Once you start sort of drilling a little bit deeper and deeper, for example, looking at that intra-urban temperature variability, you might start seeing how Hoboken might be a little bit different from Queens, right? And how the climate signal might affect that intra-urban temperature a little bit differently, probably even more so in terms of flooding. I think there's a lot of this work that might be done at the state level, for example, in the state climate assessment. And in fact, some of the projections that we develop here are part as well of the New York State climate assessment, and which also has projections for other parts of the state. So there's a little bit of intercomparison that can be done there. Although the projections here are very much tailored for New York City and the NPCC. Hopefully that answers the question.
Yeah, that's great, Luis. Thank you. There's another question here about green roofs, which I'll take since it's related to the second part of the presentation. The question is whether, even though green roofs don't have a huge retention volume, could their increased time of concentration have a big impact in shorter duration cloudburst events? And I would say yes, depending on the scale of the green roof, of course. But, and depending on the depth of the green roof as well, the fact that you are increasing the rate or the time required for water to eventually enter the drainage system, the rain has to percolate into the growing medium, and then it has to move laterally, and then it has to get into the drains, and then it has to get out of the building. And of course, if you have a vegetation on the roof versus no vegetation on the roof, the rate at which the water is coming out is much slower. So there can be an impact, not to mention the fact that actually some of these very short duration, high intensity cloudburst events may not actually be a very large volume of water. It might be a huge amount of water in a short amount of time. And if you have an intensive green roof, it's possible that there's the ability to detain that water temporarily on that roof. So I do think that green roofs can have a benefit. The question, of course, is then how many green roofs do you have in a community? One green roof may not be as impactful, or is not going to be as impactful unless you're sort of the Javits Center, which has a huge 7-acre green roof. But an ordinary residential row home green roof is not going to have that regional impact that you would have if you had, all of the roofs in the community green. So there's a back to my point earlier about a scale question there. Let's see, go back up to the top of the list. Human powered boaters. So there's a question here on changes in heat and impacts on recreation, in particular human powered boaters. I guess that's an interesting, I don't know exactly how it falls, right? An increase in warm weather might mean more recreational opportunities over the arc of the year, but it also might mean that in the peak of the recreational season, it might be too hot to recreate. I wonder if either of you have any thoughts on that.
Sorry, go ahead, Radley.
No, please, you go ahead, Luis.
No, I just was going to add that impacts on outdoor workers, like you're mentioning here in the boaters, is something that probably underexplored. And there's two aspects to this, right? There's the health aspect of the workers themselves, and there's the economic impact of potentially reduced or maybe not reduced, maybe increased if we're having more pleasant weather days outside of the main season. I think that has been a little bit underexplored in some of the NPCC work. But that's a great point. I will add that a lot of our projections are specific to outdoor conditions. So they might be a little bit more relevant to these kind of activities versus someone being an office worker, for example. But yeah, that's an interesting comment, and I'd be very curious if Radley or anyone else has heard about some of the economic costs of either from workers, not being able to work because of the extreme heat, or some other benefit because of the extended recreation season, like Franco mentioned.
Yeah, I think it's so many aspects, economic impacts, educational impacts, ability to learn in the classroom, and in unair conditioned schools, as we're seeing changes in the length of the hot season. I was going to actually go in a different direction and say, one of the unknowns is about water temperatures. That's another thing that climate models could, in theory, not be getting quite right with climate change. As waters get warmer, expect them to provide less relief, I would say. I'm not necessarily saying they're going to turn into a deadly source of heat or humid heat, but it is very plausible to imagine warmer waters providing less relief than we might have historically thought of them as providing, I would say.
And so Vivian is asking a question about adaptation, now that it's mentioned by IPCC in the most recent report. And she's asking if adaptation is factored into assessment of risk. And indeed it is, in classical sort of ways that people are looking at this. Flood risk is a function of, sort of vulnerability as well as adaptation. So, if you're vulnerable, but you have adaptations in place, then your risk is lower. So there are sort of formal ways of doing that. In the report, we don't, it's a good point, actually. I don't think that we spend a lot of time talking about adaptations. Well, we do actually. We do talk about adaptations that are underway around the city, in Manhattan, for example, along the East Side, South Street, Seaport, other places. And what we've learned from those projects. So many of those projects are sort of in the works at this point. So I think that's one of those areas where I think going forward, more research into the effectiveness of different adaptation strategies is really important. And there was another question, I guess, to me as well, on how cloudburst projects work as resilience projects. And so I think, the high level idea around cloudburst projects is to make places safe to flood. So, so that may mean increasing the hydraulic capacity of various elements in the practice, so that when there's, even if from a volume perspective, you're only, the practice that you've designed is only big enough to store a certain volume of water. If you get more than that volume of water, the water either can overflow into adjacent areas, say a basketball court or a park or a parking lot, where it can flood benignly, or you incorporate conveyance elements, so pipes, pumps, etc. Not pumps necessarily, but pipes that allow the water to pass through and go somewhere else where it's not a problem. So it's a matter of sort of thinking in multiple layers about a place and how it will respond to a flood, to floods of different magnitudes. So I think let's go back to, we only have 3 questions left. Maybe Kai had a question from about an hour ago, which we should probably get to. Did NPCC assess how city agencies are employing climate projections in decision making? And she's sort of asking for more than just how, the obvious publication of the climate resiliency design guidelines. Are there other ways that the projections are impacting decisions in the city? So that might have been a question for Haley. I'm guessing that Haley is no longer with us. Yeah, so I guess we'll have to, I don't know if Janice or anyone else wants to take that one on. Otherwise, we'll probably, it's 5:59, so we probably are sort of out of time. But I'd like to, I guess, close it and just thank Luis and Radley and Janice and Leo and Haley and everyone who helped us to to build this section, and Nikki, of course. Nikki's going to be organizing the next 2 workshops. To just sort of thank you all for your work in trying to use the CC Run seminar series as an opportunity to disseminate information that's so important, not just for the city of New York, but the larger region. So with that, I will just remind you that February 7th, and you will be getting emails from Nikki about this. February 7th, we'll be focusing on climate equity in New York City futures. And then March 6th, health and energy implications of climate change in the city. So with that, I think we'll close. Thanks, everyone, and see you next month.
Thank you.
Thank you, everyone.